Thank you, Chris. So, as I told you, my name is Kartik Samir Raju. I'm a bioresource engineering master's student here at McGill. So, not a day goes by that we don't hear about environmental issues. Global warming, renewable energy, fossil fuels, these have all become part of our common vocabulary. But, as you can see, combating climate change is only part of this challenge. How do we address water pollution? How do we address replacing oil with something else? How do we address clean electricity or clean technology? And how the heck do we do all of that without emitting any net or any increase in greenhouse gases? So for an engineer like me, it would be very convenient if we could design some sort of device to do all of these things at once. So allow me to introduce you to the microbial fuel cell, or the MFC. Basically, we're using microscopic life forms known as bacteria to solve humanity's greatest problems. A microbial fuel cell, or an MFC, basically uses organic materials such as sugars or the waste in domestic wastewater, and it feeds them to harmless soil bacteria, which consume that food just the way that we digest our own food. And in digesting this organic material, they produce two charged particles, electrons and protons. Now, the electrons are captured by our fuel cell circuit, as you can see here, and then they produce electricity. On the other side of the fuel cell on the far right, they combine with the protons and air from the atmosphere to produce water. So this is essentially a carbon-neutral process whose only output is water. So the important thing to know is that these bacteria are not altered in any way. They're not genetically modified. It's all natural. So let's put these MFCs to the test. I built my first MFC when I was 14, and I used it to treat wastewater. Researchers in Pennsylvania have built a similar fuel cell that can produce hydrogen fuel from waste. In 2007, I built another MFC that actually literally converts carbon dioxide and greenhouse gases into electricity, so that's a net zero process. And finally, I patented a discovery which uses magnetic bacteria like microturbines so that they can produce clean electricity. So not only do MFCs address all four issues, but they do it really well too. So under optimal conditions, we can produce enough electricity in a municipal wastewater tank to power 1,000 homes all year round. We can remove up to 90% of all the organic waste in wastewater. And we can produce enough hydrogen to fill up the tanks of 10,000 hydrogen cars every single day. So ladies and gentlemen, by predicting the performance of MFC technology beforehand, I'm taking the next step towards making this a reality. As strange as it might sound, but the future can be shaped by the smallest of life forms. That future is now. Thank you.
I'm wondering what you learned together as a group from this event, what you've learned about presenting your research and how that how working together was helpful.
I think the importance is that there seems to be a barrier between the public and scientific or academic research in general. I think that creates a sort of this veil or this mystique that we do things behind closed doors and we come out with commercialized products and then people just buy them and use them, or they implement something that becomes law. So I think the importance of this sort of public discourse not only helps people understand what's going on in academic research, but actually I would argue that it helps us more because it allows us to get feedback from the public whom we're trying to benefit or trying to empower as to what it is our research means to them and what are the things that we haven't looked at that they wish to see in the work that we're doing.